Okay, now I'm going to explain how motors work. To explain this well, I'll need to explain to you how an alternating current motor works, because many people really don't know how it works. It is essential that you understand it well. In turn, this explanation that we are going to give you now will help you a lot to better understand conventional equipment. So far, in conventional motors, we had 3 points to which the motor coils were connected. Any motor of any type, from a ceiling fan to an air conditioning compressor motor, had 3 points, which we called, and still call because they still exist, common point, start point, and run, work, point. The common point is common. So, how do we energize all this? Well, all of this is energized with alternating current. This is energized with one pole, this is energized with another, and from this we will leave and cross a capacitor, and we will feed the start coil, the coil with the most resistance. So, the alternating current flowed through the work coil normally, but through the start coil it flowed through a capacitor. This is a capacitor, the normal capacitor that we find in conventional equipment, which is a phase-shifting capacitor, completely different from the function of a capacitor in inverter. Why does the motor rotate? Well, the motor rotates because what I do is energize at different times. Here I tried to draw some arrows, energize different times one coil and another, towards one side, towards the other, towards one side, towards the other. So, the motor is magnetized inside and a turn is produced. Now, we only have one phase. What does this mean? That the electrons go and come back, go and come back. And we need other times too to be able to start it. If we only energize this coil, the motor would be stuck, still. For you to understand, have you seen when the capacitor is not connected the noise that a motor compressor makes? So, a phase-shifting capacitor is placed, which does what it does is accumulate the electrons here and, in an infinitesimal moment in time, then sends them. And thanks to that, one coil is energized first and the other is energized second. So to speak, it creates two phases at different times, powered by the same, but at different times. This already allows me to have more magnetic fields out of time and the motor starts to rotate. Then I will show a video that will help us to understand it better. But well, until this point we were like this. In fact, the speed of the motor, its way of working, will be given by the manufacturer, which will manufacture its motor according to the alternating current for which it is made to work. If the manufacturer made it for 50 Hz, it has to be fed with 50 because it is made for those times for the turn to be produced. If we feed it with 60 Hz, the coils and the turns will not coincide and it will have excessive consumption or directly the compressor will be stopped. This has to respect both the voltage as the frequency that the manufacturer indicates. You have to respect yes or yes. This is a motor like we were seeing motor compressors, like we were seeing fans. But in inverter this changed. In inverter it is different. Now we no longer have two windings with different resistances, perhaps 3 ohms and 1.8, but now in inverter we have motor compressors that are 3-phase, work with 3 phases. What do we refer to with this? Well, now in inverter what we will have is 3 points also, but with 3 coils exactly the same. If they are going to be 2 ohms, they all have to be 2 ohms. As the resistance decreases, they are larger motors, that is still respected as the conventional one. But now we need to feed these 3 points separately. And here, we are going to send one phase at a time, between these two other phases another time, and between these two other phases to another time. As a result, we are feeding our motor compressor with current, 3-phase in 3 different times. I make the electrons go towards one side, towards the other, towards the other, towards the other, in different times. Now, how do I do this? The one in charge of creating the electron entry, output, and output is the IPM, Intelligent Power Module. With a direct current feed, it will create an alternating current, but already of 3 phases. And so the motor compressor worked. And as the IPM is the one that creates this 3-phase alternating current, he can change the times. He can make this faster or slower, the alternation between the feeding of one coil towards another. This is the IPM, and, with a video, I will show you how a 3-phase inverter compressor works. Let's move on to that, then, in the next video. Okay, let's see in the next video how these compressors work. Every motor works in the following way. It is fed in a certain way that produces an electromagnet. In fact, if I make electrons pass through a metal as a core, that metal will become a magnet with a positive and negative pole, depending on the side to which the electrons circulate. On one side it will have more electrons, and on the other side it will have less. And that will then create an electromagnet with a positive and negative pole. If I turn the power around, what I do is polarize it in reverse. If I had another magnet, I could attract it with these electromagnets that I am creating through electrons, as we are seeing in the video. This is how any motor works. In an alternating current motor, these times are being given to it by the frequency of the alternating current that enters the home. But a controlled 3-phase motor, such as one of the inverter air conditioners, has 3 points, 1, 2, and 3, through which the electrons enter and make them circulate through the different coils. We will see in this video how it shows us how this rotation is produced. If I make the electrons circulate at different times, I will make it turn faster or slower. And that is what the IPM does. It is doing that circulation of electrons from one side to the other, from one side to the other. In the video you will see in detail how the IPM does this. Although it is simple, the important thing is that you understand how a motor works. Let's see a more complex one. And again we have 3 phases out of phase in time, that is, they do it at different times their entry and exit of electrons. As you could see, this is how a 3-phase motor works. We have 2 ways to configure it. One is like this, which is in the triangle configuration, which has more final speed, but less start torque. And then we have the star configuration, which is in which all the coils are joined at one point, so the circulation is always produced in 2, which is a way to configure that has greater start torque, but lower final speed. 3-phase motors have these 2 ways to be configured. The third cable is left unused. It is the one that is used as the Hall effect sensor, because the third cable has a coil that is not energized. And as this coil works like a motorcycle pump, as we have been talking about, all the coils work like this. What it will do when it is energized, but with a little magnetization, is to finish discharging that magnetization in the cable that is left free. Then, the IPM detects it and can know at what point there is an empty point and know if the motor is or is not rotating properly. The third cable is used as a rotation sensor. Through this video you were able to see how a motor works. Now we will see how this is produced in an IPM to make a motor rotate at a different speed. Let's go to that. So, what is an IPM inverter and how does it work? Let's talk about that right now. Looking at the board, the IPM is the component with the most terminals in an inverter unit. It is located exactly after the capacitors because it is powered by the voltage that the capacitors have filtered. The output of the IPM goes directly to the compressor motor. For example, let's look at this track tracing on this LG board. We have an IPM powered by capacitors. The negative of the rectifier goes to the capacitor. The positive of the rectifier goes to the capacitor, which filters the voltage. After that, we go one way to cross these resistors that work as a fuse, which are resistors with a very low resistive value, and we enter the IPM. On the other side, from the other output of the capacitor, we cross these 4 lines that are jumpers to jump that track, and we are also going to power the IPM. At this point, we have the IPM exactly. In fact, if I show you an IPM, you will clearly see that it is located in that way. This goes, of course, upside down. On one side, we have the connections a little thicker, and on the other side, we have the thinner connections. For now, we are not going to talk about this, but we are going to talk about the thickest. We have a positive and negative supply of the rectified current. In the middle, we then have the 3 outputs that will go to the compressor. We feed with negative and positive, and with 3 outputs we go to those 3 cables that I connected as a test of tests that we will do later. But if we look from the other side of the board, it is the tab where the 3-phase compressor motor is connected. Well, you saw the whole journey that electricity takes on a board to reach a compressor motor. And we still need to understand well how the IPM inverter works. We still have to understand that point well. And now we are going to go to that. Physically, this is the component, which is glued to the heat sink. It always gets very hot when creating that 3-phase current. Now, with a small diagram, we will understand how it creates this 3-phase current. It is very simple, you will understand clearly. Using this diagram, we will understand how an IPM works. The first thing we need to do is to identify the inputs and outputs. We are always talking about electrons. Remember that electrons enter through the negative terminal and exit through the positive terminal. And at this point is where we have the DC power supply of 310 or, depending on its voltage, 155 or 180 volts in DC, which comes rectified and everything prepared to create it in 3-phase. This device will transform the DC current into AC. That is why the IPM, the main component that gives the name to the inverter. Well, at this point we had the input of direct current, but in these 3 points U, V, W, that is how a 3-phase voltage offset is represented with those letters. They are not abbreviations of anything, not even the initials of any word, they simply point to a sequence that we have connected in these 3 points. Well, in those 3 points it is known where the coils are connected. We have a coil here, we have another here, and here we have another. And what we have to do is that between those 3 coils of the compressor motor, let's turn or pass the electrons at different times. We have to make the electrons go in that direction, and we also have to make the electrons go in the opposite direction, and at different times. How does this happen? Well, here we have 6 points that are going to enable 6 electron bypass keys. They open and close, and all this at different times. What happens, for example, if I open this key through a notification at that point, and I also open this one? If I open this and open this, the electrons will enter through here, cross this key, and exit through here. Then, by deduction, they will cross. Sorry, I drew this point wrong. By deduction, they will cross the coil that is between U and between W. They will cross this in this sense. Now, what happens if I don't want the electrons to go from U to W, but to go from V to U? Well, that is also simple. What I have to do is, instead of opening this and this, now I have to open this and this. Then the electrons will enter through this side. They will enter through there, the gate that is open. They will cross from W and they will go to U because this is the one that is open to exit. We cross the same coil but towards the opposite side. If I open these two, the electrons enter and exit through here. If I open these two, the electrons enter and exit through here. If I open, for example, this gate and this, what will the electrons do? Well, the electrons will enter through the side that is allowed, and they will exit through the side that is allowed. What coil will they cross? They will cross U to V. So, they will cross U to V. If I want to go from V to U, if you want to go backwards, and well, these two are reversed and open the opposite ones. So, in that case, I open this and this, and the electrons will enter through this point, cross from V to U, and exit through the positive. We always enter through the negative and exit through the positive. That is always the case because there is DC, but I make the electrons pass from U to W, from W to V, from V to U, from U to V. I change their direction by opening synchronously different gates. And this is how the three-phase current is created in an inverter compressor. One important detail is that even the compressor motor is part of the electronic equipment. The compressor motor is part of the electronic equipment because for the circuit to finish working it needs the compressor. This is why an inverter it is so complex, because even the last coil of the compressor is an integral part of the electronic system of the entire electronic circuit of the equipment. That is why we cannot make inventions like placing any compressor, any IPM. Everything is completely synchronized and configured, and everything in order. Now, look at the points that I am going to mark now. Let's see. Let's tidy it up a bit. And we will mark with red the points of the IPM of the thick side. That is, these points that I am going to mark now are the thick side of the IPM, the side that the voltage enters and the strongest voltage leaves. But, what is all this? Well, all these points that come from the microprocessor, a delicate part of the board, are the ones that I am going to mark now with green. They are the notices, so that perhaps the gates open at the time that the microprocessor wants. They are also sampling points of the input of the electrons to the different differentials of the different gates. These gates, in reality, are IGBT. It is a special form of transistor to support high current and high speed. They are also not JVT or MOSFET, in case anyone asks. They are IGBT, and they are powered with 15 volts. We will talk about this later, but I will tell you in advance, they are powered with 15 volts and there opens the gate and lets the electrons pass. I will explain this later. All these green points, and we still have more. We also have here, and look at these are direct samples of U, V, W, and here we have two more. All these green points are these sides. This side, excuse me. It controls how the electrons enter, controls how they exit to the coils, controls the state of the coils, activates the gates, and measures the temperature. It is a complex circuit that is in direct contact with the microprocessor. This is how the IPM works, creating the three-phase alternating current for this three-phase motor to work. Depending on how it opens these gates, at what time it does it, the compressor motor rotates faster or rotates slower. Excellent, this is the circuit here as we see it. Now we will move on to seeing it on the boards, and then we will move on to controlling this component to know how it is measured. One detail that I want to mention before finishing this part, these diodes, how these gates open and close constantly, a spark is produced. These diodes, in this position, consume the spark so that these gates are not damaged quickly. These diodes consume that energy, and they are always placed between the output of the compressor and the negative and positive poles, but of course they are placed in reverse, indirect. We will talk about that later, but that was the component that I needed to explain to you. Now, let's go on to see it on the board and make measurements on the IPM and also on a three-phase inverter compressor motor. So, at this point, what we are going to do is to check the state of an IPM but on the electronic board. For that we have the following images and also a previously recorded video that we will analyze together. Take a look at how this measurement is being done. The first thing we have to detect is which of the poles of the IPM is the positive and which is the negative. Remember that the idea is to control all this with the equipment connected, but without having to disassemble it completely, with the equipment installed without power. You will only see this side of the board. So, we have the capacitors, we have negative and positive pole, and what we are going to do is to search for continuity between the positive pole and the different points of the IPM to find which is the positive. We are going to put the multimeter in continuity position. Keep in mind that this is very well varnished, so you will have to find points where you can make measurements, such as these small perforations. These perforations are to pass with the continuity or with the track from one side to the other of the board. They are perforations that allow us to make measurements. So, we put the multimeter there and in the different points of the IPM to see in which one it gives continuity. We will continue with the video. We see that there is no continuity and there is continuity. Well, there we have identified one of the two poles. We were able to identify the positive or the positive input to the IPM. We continue, we move on to the negative side. We are measuring from the negative of the capacitors and we are going to control on all the different points to see with which one we have continuity. And there we can already see it, it has continuity with the first. So this is the negative input. Very well, what are we going to do now? We are going to put the multimeter in diode position because what we have to do is to control these diodes. Remember that here we were with these diodes connected in parallel to the IGBT, and what we are going to do now is to try from the positive towards U, V, and W. What are we going to be controlling? Well, these must be completely open. There should be no continuity. Usually, when they burn out, they go into short circuit. So we try in diode position. From W to P, we are going to measure this diode, and that will give us a parameter that internally the IPM is in good condition. We will go from W to P, also from V to measure it is diode, and also from U to measure this third diode. We will not control the IGBT at this time, because it has a high resistance, it must be open, and when it burns out, it usually gets stuck. So what we are going to do is to control this diode in parallel to be able to check its state. And the same we will do from negative. We will go towards U with a negative also towards V, and also towards W, checking in diode position the multimeter, always checking the value of this diode that we have here. Well, then let's see how in the video we do just that. The resistance, or rather, the voltage drop of the diodes, will be the same as all the diodes, only it will be a little higher because they are diodes with more electron flow that support more current, so the voltage drop is even lower. Let's continue with that. We advance a little in the video, and notice that we are not measuring from the IPM, we are measuring from the capacitors, towards W. We know that this goes through the IPM, we already know that. So we have then between positive and W, placing the electrons from the positive, we have the voltage drop of a diode. Energizing or sending the electrons from the positive to the W, now from the positive to the V, we also have the voltage drop of a diode and also towards the U. We sent electrons from the positive to U, V, and W, and the voltage drop of a diode appeared. Returning to the diagram, what we did was send electrons from the positive to U, V, and W, and we clearly see that the diodes are placed in direct, the electrons must pass. So far, we are good. We continue advancing, and what we are going to do now is to invert, and we are going to send the electrons from the other side, from the U, V, W. Notice that here we have the negative, and although at first a small data appears, then what happens is that it opens. So it remains open as it should. The electrons do not pass through those three diodes. Well, to this point, from the positive, or rather, from U, V, W to positive, the diodes are in reverse, then we mark OL. Now what we are going to do is to go from the negative, because we also want to test the other three diodes. What we want to do now is to test from the negative to U, V, W to test these three diodes, and with them the three IGBTs. Now we are going to go to the negative, and sending the electrons from U, V, W should give me a voltage drop. We send electrons from U, V, W to the negative, and the diodes are in direct. We take it well. And now what we are going to do is to invert the cables, and in this case the electrons do not have to pass because we are going to send them from the negative to U, V, W. Now we have an open line. Well, with that we are controlling quite a bit of an IPM. Of course, this is the voltage-free test. We still have the voltage test, but to this point we are quite advanced. We are testing this component that is the IPM, a component that is damaged a lot because it handles a lot of power. We were testing it in this way, in function of diodes and without disassembling, which is key. The idea is that you learn to do those measurements without completely disassembling a board. Well, let's keep going. Here I have an IPM that I wanted to show you. What we tested was the IPM, which goes placed like this, but from the other side. In this case, we have an IKCM15F60GA. This is the model of the component. Don't worry, later we'll talk about how to acquire these components. We'll talk about the price, how to have them shipped to you. So don't worry, we'll talk about it a lot. Excellent, this was the voltage-free test. Well, up to this point then, we have been seeing a fairly simple IPM diagram. But let's see a slightly more complex diagram, which is not actually more complex, it is how a diagram of an IPM really is. In this case, we have the same model that we physically have here. It is an IKCM15F60. If we look at it, it is a more complex circuit than what we have been seeing so far. But basically, the power part, obviously, is the same. We will have the 6 IGBT. We will have, from its control circuit, the warnings to those IGBT. These are warnings that will cause them to activate. Every time we press on those points, the IGBT will activate and will let electrons pass. I don't know if I mentioned it, but with 15 volts in direct current is how IGBT are activated to allow current to pass through. And from the other side of the delicate part, well, here's where we have all the control zone. Let's say that all this goes to the microprocessor. And from this side, thicker, well, we have P, U, V, W, and neutral separately, which in the end, inside, are joined together. This is the input of the electrons, so it is a bit more robust and has more terminals. Well, this is an IPM. It is the most complex circuit of an IPM. It is not necessary to understand all this operation of each component that is within its integrated zone to understand how it works. But I do want you to know with this that not all IPMs are the same. Not all of them have the inputs in the same place. So, what you have to understand is that you cannot replace it with just anyone. You have to put exactly the same if you do not want to modify the electronic board. Attention to that detail. You have to buy the same one to be able to place it in the place where it corresponds, and that each terminal coincides. Keep that detail in mind. Very well. This is an intelligent power module. Attention that this is an IPM, intelligent power module. It has a complex circuit inside that, in reality, is not the one that is most damaged, but the one that is most damaged is the area that handles the largest amount of electrons. The area that handles the power. This is the area that is most damaged, and that today we already learned to measure. Well, let's see then how this works. But let's see it with the equipment running. We will do the IPM tests, but with voltage. Well, basically, what the IPM creates is an alternating current. How does it create it? Well, we've been talking a lot about how it synchronizes the gates to open. Finally, it ends up creating a three-phase alternating wave. Let's see if we can draw it correctly, as follows. Okay. This is not how it creates it. This is what the motor understands. In reality, what the IPM is going to create are pulses, always of the same height. In reality, it does not create a sinusoidal wave, but rather it creates pulses that the motor eventually understands as sinusoidal waves. So, we're going to draw it like this so we can understand what we're going to see later on the oscilloscope. One detail I want to mention is that the peaks of these waves are always 310, and that is because we have 220 volts. These are always the peaks, even if they don't show up in the drawing. The peaks are always those. And now we're going to erase the sinusoidal wave that is not actually there. And something like this is created. Electrons enter, exit through different paths. The same in another time. And the same in another time, which would represent the red. This is what makes the inverter motor rotate. And this varies in frequency and becomes shorter, wider, shorter, wider. Okay, we're going to see it with the measurement we're going to see now. Look then, measuring with the oscilloscope or working compressor. Let's see if we can see. We're going to place the oscilloscope between two of the points, between V and U. V and W are the same. And we're going to turn it on. We can see how that frequency is starting to be created through pulses. It doesn't look good there, but we're going to press the automatic key and calibrate the time. And we're going to put it in a position where we can see and understand everything we were explaining. We're changing the time that the oscilloscope shows. It looks much better there. We're only seeing one phase because this oscilloscope is only one channel. If we placed it in any of the other forms U, V, W, in any way, we would see the same, but at different times. Notice that the frequency at which it is working is actually almost 1000 Hz. What is commercially said that an inverter works with 15 to 120 Hz? Well, in reality, it is something commercial. In reality, the frequency that the IPM generates is higher and ultimately ends up creating a sinusoidal wave of less frequency. What this is measuring is each pulse. We can see it better there. This cannot be measured with a multimeter. The output of the IPM cannot be measured with a multimeter. I'm going to show you now in a slightly more stable video how the compressor accelerates and decelerates. There we have it running at minimum revolutions. It's a long video, so I'm not going to play it in its entirety. But notice how the time it takes from one wave to the next shortens. We put more cold on the equipment so that it spins faster. We asked for more cold. And notice how it starts to shorten. They start to be closer together. That is, the simulated sinusoidal wave that is created gets closer. And there we would be almost at maximum speed. We are always respecting the RMS voltage. It is always respected because it is an average. Because a simulated sine wave is eventually created. The maximum is 324. We are well at 310, only that there was a little more than 220 at this moment and peak to peak 650. The voltages are always the same. The voltages are the ones that enter through the line of your home, if you go back to the class where we measured the rectifier bridge. The values are the same, only now, through pulses or square signals, we are creating a sine wave that we can modify the time. And then the compressor starts to run slower again. We again make it slow down its speed. There it slows down again, let's see. I don't remember well, but I think we stop it here. We stop it at minimum speed. And now the compressor stops. There we run the time to be able to see better. And there it is off. Well, and there we have the compressor. In fact, no, it hasn't turned off yet. I'm wrong. The compressor is still running. What we are doing is changing the time with the keys of the multimeter of the oscilloscope. We are changing the time. That's what we're doing. But well, the idea was well seen. So, as the compressor running slower has a more distant simulated sine wave, and once we start accelerating we have it much closer together. Well, I'm going to let the video run a little so you can appreciate the acceleration a little more, but in real time. We will see from here, and we will leave a few seconds so that you can observe. The only way to be able to see this is with an oscilloscope. A multimeter does not give me this possibility. A normal multimeter gives me the possibility of measuring direct current or alternating current, but 50 to 60 Hz. Only an oscilloscope gives me the possibility of visualizing and understanding this. And that is why only an oscilloscope is going to give me the possibility of being able to detect, in case of failure, if the problem is the motor or the board. I can only do it with an oscilloscope. This is the work of the intelligent power module. Okay, now let's see how to measure the resistance of the coils of an inverter compressor. We will see it through a video. Let's observe how we place the multimeter in resistance mode. And, as they are three-phase and the phases are electronically offset in an intelligent way, the coils must all be the same. The resistance must always be the same. Here we have 2.3, 2.3, 2.1 ohms. The multimeter always produces a loss. Again we have 2.2, 2.1. And with the third measurement we have to have the same value, 2.2, 2.1. This is a good working inverter compressor. A small detail to keep in mind: if the capacity of the compressor is larger, the resistance is lower, because its windings are thicker and offer less resistance. And the same in reverse: smaller capacity, higher resistance. The data we just saw corresponds to a compressor that works with 310 volts and DC, obviously controlled by IPM, but 12,000 BTU. That is, 12,000 BTU or 3,000 calories, as it is said in other countries. We are talking about approximately 2.2 ohms each in its coils. This is how we check electrically and without voltage that a compressor is in good condition. Of course, we always have to always make a measurement between the coils and the ground. Always make a measurement like this, and it has to show OL. Of course, it should not have a ground discharge. In the following video, we will be discussing how to check if an IPM is in good condition when a motor is in poor condition. When we already know that it does not work with a motor in poor condition, what we most want to identify is to know if the board is still working or not. How do we know if the IPM is working or not working? Of course, we will be measuring the IPM. We will be measuring the diodes. We will be seeing that it is not in short circuit, but we want to see it working. We want to see it acting, to make sure that everything is fine there and to be able to change the motor with peace of mind. Well, it is done in the following way. Let's see then the measurement of IPM with oscilloscope, but without the motor connected. There we clearly see that the motor is disconnected. And we will see the data that they give us in the oscilloscopes, which ensure that that IPM board is working well. Let's play the video and see what happens. It is fast. This measurement is very fast. We energize the equipment, turn on the air conditioner, and a moment will come when the IPM will send electrons. Well, what happens is that the IPM sends electrons on one side only and does not receive them on the other because there is no coil that connects one end of U with a W or V with W. So, it needs the compressor coil to be able to return. We need the coil for the electrons to return, and as it does not have it placed, the electrons will be sent on one side only and will not be able to go to the other. So, what we are going to observe is what we just saw: the electrons push to one side only and then it cuts off. Of course, it is not the full voltage. You will always see a lower RMS, because it sends some pulses to see what happens, and as the motor does not start, it quickly cuts off and marks an error on the board. There we can see that the IPM is in good condition, at least in part. Because I say in part, well, because this same test that we have just done here, we have to do it by testing. first inverting V with you, the poles of the oscilloscope. Then, we have to test in V and W, and in U and W, we have to test the 6 different combinations. In this way, always seeing that the electrons go to one side, we confirm that the IPM is in good condition. One more detail, depending on how you place it, there are 3 configurations that the wave will appear down, and 3 configurations that the wave will appear up because it sends the electrons from the other side. So this is how we check that the IPM is in good condition when we don't have the motor connected, when we already know it is defective. How do we test if we are in doubt that the board does not work? How do we test a compressor without the board to know that it works well? Well, we will see that later in the universal board class. Later, doubts will be cleared up with respect to tests if we have boards and the burned motor, and we do not have a motor if we do not have a board. Little by little I am explaining all this in the training so that there are no doubts in something important, to be able to give a correct diagnosis to customers. We don't want to say that the motor is the problem and once we put the new motor in, the problem is the motor and also the board. We will talk a lot about that. Don't worry. Well, that's it for this class. Very well, at this point, what we want to explain is how the IGBTs are powered with 15 volts, or rather, what is the path of those 15 volts. So, we are going to follow up. This is going to be brief, but the idea is that you can identify and recognize them. There is a component in that area that is often damaged, and when this component is damaged, we have an error in the IPM, but the IPM is not the problem, but the component that is responsible for maintaining those 15 volts constantly. Let's observe it in the following way and see if we can identify it. Let's go this way, leaving the switch mode power supply. Let's zoom in on this area. There it is, here where we have the transformer and the other side of the switch. Starting from here is where we generate the 15 volts. These 15 volts, notice that we even have a checkpoint here. Here we have the 15 volts. They are derived on one side to this point. This is the fan inverter connection socket. We will talk about that later. And notice that these 15 volts follow a path. I went off the camera, sorry. They follow a path and reach these points. These points are for transfers. Through these perforations in the board, the voltage is allowed to pass to the other side of the board when they are double-sided base plates. Now we are going to the other side. Arrived at this point, in this area. Let's see if we can put a little more light. What is done now is to go from here to these points that feed the capacitors. These capacitors that we are seeing here are responsible for maintaining the 15 volts to power the IGBTs. These are the capacitors that maintain those constant 15 volts that will be injected into each IGBT as appropriate. An error or deficiency in these capacitors will cause us to have an IPM, motor, or overcurrent error. We will not have an error on the board that tells us the IGBT power capacitors failed. No, this error we will have to deduce ourselves when the problem is in the motor or IPM area. So, if we control that the IPM is in good condition, we can move on to checking these capacitors, and it may be that we find the problem there. Well, these capacitors are type SMD. This means that they are soldered on one side of the board, they do not pass through to the other side. So, to disassemble them, we have to heat with the soldering iron in this point and in this one. And these capacitors come out. Later, in the soldering practice, we will be explaining how to use solder and a soldering iron. So, don't worry about that. Well, the problem with these capacitors is that they are in different parts of the board. For example, in the case of this board, we can make a measurement of those 15 volts that is located in this checkpoint without disassembling the entire equipment completely. Just by opening the outdoor unit, we already have this area exposed. We can do a test between 15 volts and GND in some checkpoints, and we will see that we have the 15 volts. But to know that those 15 volts do not fall on the IGBT power point is complicated because our test point is on the other side. So, in these boards, it gets quite complicated. Unless we identify the 15 volt points on the IPM, but for that we would even need to know what model of IPM we have here. So, these capacitors are complicated to check on these types of boards. So, if we suspect that there is this problem, we have to remove the board and test it outside. When we see the test of the complete operation of the equipment, we will be seeing how to measure those 15 volts with the equipment assembled, but in a model that can be reviewed, which is the one I will show you next. We will see the board of an LG inverter and see that the power capacitors of this LG are very visible. In fact, if we look at the board from above, at this point we will already have the test points of those 15 volt capacitors. Clearly there are capacitors here that go directly to power the IPM that is in this area. In this case, we can measure the 15 volts without completely disassembling the equipment, not even taking out the board. And here are the capacitors that keep those 15 volts. Moreover, they are much simpler capacitors. I will now show you a carrier brand board that is a media board installed in a carrier or media unit as well. We will see that those capacitors are even more complicated to check. One moment please. Let's see then a media electronic board. Let's see if we find the image where it is clearly visible. There it is. Please observe here. To access these capacitors, we even have to remove the heat sink. This is a board viewed from the bottom but with the heat sink uninstalled. In these models, we even have to uninstall the heat sink. So it's even more complicated. But well, know that it exists. That we have to test their capacity to be correct. And that the best thing is to see if those 15 volts are maintained there or a little less with the equipment in operation. When it is working, a little less than 15 has to be maintained. Well, then know that this is there and that they tend to fail quite a bit. Not only in inverter air conditioning, but also in refrigerators, fridges, or refrigerators. Excellent, having seen this, we will move on to the following topics. Very well, we will continue with our training and from now on we will talk about fans or forcers. In inverter technology we will no longer find only AC fans, like the one we have in hand, but we will also find triphase fans or forcers. To summarize, we could say that we will find 3 different types of forcers. These are AC forcers, which is the one we have been finding in any air conditioner so far and which are also found in inverter technology. We will also find DC and U, V, W forcers, these two being of the same operating mode, only a little different in the way of making them work from the board, but they are exactly the same. They are fans or forcers whose winding is 3-phase, just like the compressor motor. Very well, let's start then by talking about the simplest one, which is the AC forcer, which is the one I have in my hand and I will show you right now. This type of fan has an AC power supply. What does this mean? That we will be directly feeding it with 220 volts or 110 or 127. A small phase shift capacitor will be placed. We had already been talking about this when we talked about how an AC motor works. it will have a rotation frequency of 50 or 60 Hz. The manufacturer already made the coils so that with a certain frequency of electron circulation the motor can rotate and function properly. So, it will always work according to the voltage we have on the line and the electricity. The board will only do is somehow send it that voltage. But the voltage of this motor from the board is not sent only through a contact relay, as the fans were previously powered. Now we don't have it. These relays are for working in fans with multiple windings that make them rotate at different speeds. But in the case of these fans, if we glued it with a relay, it would always rotate at maximum speed. So, we need some kind of circuit to be able to make it vary the speed. We are talking about the indoor fan, How is this change in rotation going to be produced? Let's keep in mind or think first of some parameters. What can we not do to vary the speed of this fan? Something we can't do is vary the voltage or frequency. So there we already have two things we can't vary. Because the voltage is already pre-established, that fan, at least the one we just showed, is 220 and the frequency is 50 Hz. If we vary the frequency, it will consume more electricity because the electron circulation will be confused with the rotation. And if we vary the voltage, the same. That winding will demand more electron flow due to the lower voltage and the amperage will rise, and with that the heat of the motor. So, since we can't vary these two data, how would we do the speed in a fan of this type? Well, this is produced through a circuit. The circuit that is used for this is this one that we see here on the board, which is obviously near the area where the fan is connected. This circuit is composed of some resistance, some filter capacitor, a triac and an optocoupler, as well as two power resistors. Optocoupler and triac are the main components. These two can be combined to form an optotriac, which would fulfill the same function. Now we will explain in detail each of those components. Don't worry. Well, what function do these components perform and how do they vary the speed without modifying either the voltage or the frequency? Let's understand it without any inconvenience. We have a frequency that we cannot vary, neither the voltage nor the frequency. What is that triac going to do? That triac, which is like a kind of electron switch, that triac has a power supply at this point. It was going to let the electrons pass from one side to the other, and also from one side to the other, depending on the moment in which it is powered here. When a voltage is injected at this point, on this surface, the electrons are allowed to pass to one side and to the other. That is a triac. Unlike a transistor, which only allows passage to one side. We will see more about that later. So, when does it activate and deactivate? This is where the board needs the zero crossing detection. At this point, the microprocessor needs to know at what moments in time we cross zero. And that is where the importance of zero crossing detection comes in. These waves are symmetrical in the same way, but well, here it comes out a little more open. Don't pay attention to that. Why do we need zero crossing detection then? What the board is going to do is that, when the zero crossing is detected, the application of voltage to the triac is cut off. So, no voltage will be passed to the fan. It will wait for some milliseconds to pass, and then it will activate it. Then yes, voltage will pass from this point to the fan. All the power of that piece of the wave will be applied to the fan. When it crosses 0, the triac will deactivate again and will wait again for a certain amount of milliseconds that we will say are 3 milliseconds. 3 milliseconds are waited and then the voltage is injected and all this electron power is injected to the fan. When it crosses 0 again, the same thing happens again. The power is cut off. 3 milliseconds are waited and then we apply the voltage again. If you think about it this way, look that if we talk about 3 milliseconds, here there are not 7. And in total, in a whole cycle, we have 20 milliseconds. According to the 3 plus 7 plus 3 plus 7, we have 20 milliseconds. These 20 milliseconds happen 50 times in a second. This is how the fan speed is regulated. If we wanted it to go slower, if we configure it at a slower speed, well, instead of waiting for 3 milliseconds to pass, it will wait for 7 milliseconds to pass. It will wait for 7. So, it will only apply this power to the fan. When it crosses 0, it cuts off. It waits for 7 milliseconds to arrive, and only 3 milliseconds of time are applied to it. It waits for it to cross 0, it disconnects. It waits 7 and at that moment it applies from when it crosses 0 to wait 3 milliseconds, 5 or 7 milliseconds to turn back on and inject the electrons again. We need zero crossing detection because if not, there will be confusion between one side and the other of the electrons. It crosses 0 and when it activates, they are sent to one side only and then it is cut off. Then they are applied to the other side and then it is cut off. And then they are applied to the other side and then it is cut off. And the electrons go one way and come back, stop and come back. We do not vary the voltage which remains the same, in this case, a peak voltage of 310. Nor do we vary the frequency, because we are not shrinking or moving away the electron sending. Respecting voltage and frequency, we can have a speed variation by sending less electrons. This is how the speed of an AC fan is regulated. These fans, of course, also need a capacitor to work. They are motors that we have already been analyzing, of alternating current of 220. We would not see the frequency or the voltage. Here are the coils. We will see all this, but we will go on to see it on the board. Well, then we are going to see in the electronic board everything we have been describing about how the fan works and how its speed is regulated. Well, we turn on the light and now, please observe this part of the circuit, of which we have it very clear. Here we have the dephasing capacitor of 1.2 microfarads. This can also be the reason for failures if the fan does not turn well. It is removed and a new one is placed to test it. And we have here the circuit we were mentioning. Well, as this speed is regulated, we need an optocoupler because the integrated circuit has to tell it at what speed to turn. So, we need an opto to make a dielectric division, that is, so that what happens on this side does not affect the microprocessor, and it does not get burned by the high voltages that are handled here. So, let's observe the following. Here are pulses generated at the moments when they have to turn on. The optotriac is powered, which connects from the other side. And there is where then, through this resistor, a low voltage is injected at this point of the triac. And the triac will do a connection. Look at this side. Here we have the line, and here we have the neutral. Here we have the line. And the line will feed this point of the triac. This line will also come here, through this resistor to reduce that voltage a bit. And when this point is connected, thanks to the fact that this light turns on, this terminal of the triac will be fed, which will allow these two to connect, and the middle point of the fan will be fed, which will be the common. At the same time, on the other side, we have the neutral that feeds the working coil, and through the capacitor that is in this rectangle, the starting coil is fed. And this is where the cut and the on are produced, those 100 times per second, constantly. What elements can be damaged if this does not work? Any of these. That's why we're going to check them one by one. In the case of resistors, we will check their resistance value. In the case of the optocoupler, we will be testing the lead and also the other area of the circuit as we have done previously. And in the case of the triac, we will be testing directly that there is no short circuit between the two gates, or rather, between the two sources. Well, then we are going to check it in the following way. We place the multimeter in resistance position and we are going to measure from the side of the triac. We are going to measure it from the other side. We have to have a high resistance of megohms to know that everything is fine. There it is. Let's try it this way. And then we have a very high resistance that even goes to open line at this point. We are fine. We are with open lines. Now, testing towards the one that energizes to activate, we will have a resistance, which is derived from resistors that we have placed here. These resistors are in good condition, 500 ohms and 100 ohms. And here we have the optocoupler, which we have to test its light side and its opposite side. Remember that the light side we will test in diode mode. And there we have the voltage drop of a lead, 1.12 volts of drop. We are going to invert and we have the voltage drop of the diodes that are on the opposite side, forming part of the variable voltage circuit, which are the ones we have in the driver that is the one that will energize it. Very well, this is how we are testing all the components of this voltage variable circuit through the wave cut, based on a zero crossing detection. Any problem in the zero crossing detection, what we will have is a fan error. It will not work, it will mark an error or it will tell us directly the plaquette. If it is more sophisticated, it will tell us zero crossing detection error. This is how the speed of these fans is regulated. This is the way it is done electrically, and we can measure the components without voltage as we are doing now. And we can also measure this with voltage as we are going to do. Well, to measure this with voltage, what we have to do is place between the neutral and the line that is the one that comes from the triac. Between the neutral and the line, we have to place the multimeter in voltage and alternating current, since it is an alternating current of 50 Hz or 60, and this will mark us a certain average voltage. These voltages will vary depending on how many electrons are sent, and what a multimeter will do is to take an average. So, as a result, what we are going to see finally, controlling voltage between this point and this, which remember that here is cut through the triac to this power. Between these 2 points we are going to be finding, in low speed, a voltage of approximately 167 volts. In medium speed, approximately 185 volts. In high speed, approximately 205 volts. Always talking about 220 volts, what a multimeter will do and take an average, and since the wave is being cut, it will believe that the voltage is lower. In reality, the average voltage or the force that is sent to it is lower. This would be the voltage test. Remember that you will find these circuits in conventional ones, in most of them currently, and in inverters you will find them in many, especially those that are 9,000 or 12,000 BTU, or in Fragorias, we are talking about 2,250 or 3,000. Very well, One more component that I want to mention is that, sometimes, instead of an optocoupler that feeds a triac, which allows 220 volts to pass. Here we have an optocoupler, and here we have the triac. Here, instead of finding these two components separately, you can find them together. When you find them together, we are talking about an optotriac, and, in that case, we are talking about a component that has a LED on one side, and on the other side we have a gate that allows the passage of 220 volts. They can also be found in this way, and the component encompasses all of this. Always, to be able to identify these components and know how to measure them, remember to look at their patent. In other words, remember to observe the number that it has on its component. In this case, we have a Mach 3021. Well, this is an optocoupler. Perfect, then I will show you a plaquette that has an optotriac. On this plaquette, we are seeing directly a power supply from the microprocessing area, and through these tracks we go directly to this component, which feeds this LED, and on the other side, directly, allows the link of the 220 to power the fan. Notice that directly from the LED, right there is where the 220 pass through and power the fan through this connector. Here we have then an optotriac. Here we have it all together, all assembled. Okay, so far with the way to regulate the speed in these fans. Is there anything else? Yes. How does the electronic board know how fast the fan is spinning? This function is not fulfilled by these three power cables, but by the three additional ones that you often see. They are a Hall effect sensor. Through these three terminals, the board knows how fast the fan is running and sends it more or less electrons through the circuit we just analyzed. In the next video, we will talk about the Hall effect sensor and how it works. Okay, so far we have been talking about AC fans. There is another parameter that we need to take into account, or another part of the fan that is also very important to function properly. In addition to the power cables that we have already been analyzing, as well as their path on the boards, we also have three additional cables that represent the Hall effect sensor. These cables allow the fan to inform the board at what speed it is rotating and whether or not it is rotating properly. It is a kind of sensor. Now we are going to explain how it works, how it is used, and how to make the appropriate measurements. This is important because if a board tells us that a fan is not working, it may be that, although the fan is rotating, the Hall effect sensor is not working. In fact, this is something that is damaged quite often. So, how does this sensor work? In this case, on this fan, we have printed on the side what each of those cables means. On one side, we have the yellow cable, VCC, the brown cable, BRN, which would represent the negative, and gray, output voltage. VCC and BRN are the power supply for this Hall effect sensor. It is powered by 5 volts, and this is the negative. And the one below is the output pulse that will notify the board as the fan rotates. So, let's diagram this and understand how this Hall effect sensor works. In reality, it is not a circuit in itself, or in other words, there is not an electronic circuit inside the fan. It is a kind of magnet that is doped in a certain way that allows for a certain notification. In fact, I will explain a little more now, but to be able to understand it. When we talk about a Hall sensor, we are always talking about a sensor made or created through a modified magnet. It works in the following way. To explain it in a simple way, it works like this. We have a magnet that, on one side, is polarized with what we saw was called G and D, which is the negative, and on the other side, we had seen VCC, which represents the positive. So, the positive enters this magnet and the negative also. Inside this magnet, there is a strip of electrons that are circulating through its center. But what happens? When we pass certain metal through this point, what happens is that the electrons move out of place. Let's say they move to this side and allow a positive pulse to exit from one of the sides. And this third one is the V out, or the output pulse. Okay, we are talking about 5 volts of direct current. Here we have the negative of the 5 volts. And at this point, we will also have 5 volts every time a metal passes by, but these will be through a pulse. Why? Because this metal will pass by here, but this is the fan that is rotating. If we continue to complete this drawing, it would be something like this. Do you understand? As the fan rotates, each time it passes through these metals, it attracts electrons and allows a pulse of 5 to go out through the output. And with this pulse, then, the board knows that the fan is rotating correctly. Well, that's how a Hall sensor works, both in air conditioning and in other circuits. The way it works is the same. By means of a magnet, we produce an output signal. Well, we have to test this circuit because what usually happens? Well, this magnet can break. This area can be filled with metal slag. Let's suppose that it doesn't break, but this area is filled with metal slag, which does not allow the electrons to be attracted when the metal passes. Well, all of that can happen, so we have to do a test. Our test will be the following. We will inject 5 volts and see what comes out from here. And we will do that with an LED. A very important detail that we have to keep in mind before is that the voltage input, the negative, and the output are not always printed on the fan. There are times when we don't know. In this case, we did know that this is the yellow cable, the negative the brown cable, and the output voltage in the gray cable. In this case, we did know which was which, and in fact we have them here with the 3 colors that correspond. But sometimes we don't know which is which. Sometimes, on the board, there is only a diagram of the following way, and it doesn't tell us anything else. Well, in those cases, first we have to go to the original electronic board and be able to identify which cable is which to then test this circuit. We will do that by simulating that. In this case, it would not have indicated us. Well, we will run a little bit of our plan and measure our pieces. Well, this Hall effect sensor is connected at this point, at this terminal, and in this position. To be able to identify which is the positive and the negative, if we did not have the small diagram on the board, the trick is the following. We put the multimeter in beat mode, which makes a beep when there is continuity. So, we go to the 7805, which is the one that generates the 5 volts, to the right point of the 7805, and see which one it has continuity with. Brown. No gray either. Yellow. Yes. There we have continuity with the yellow. What does that mean? That the yellow is the 5-volt power supply to the Hall sensor. Now, we go to the negative of the 7805, which is both the middle point and the case. And we try again. We try the yellow, just in case. No. We try the gray. No. We try the brown. Yes. It is the brown and the positive power supply. And the gray, by deduction, is the return signal. Once the three are identified, we take notes, draw them to be able to memorize. Remember that yellow is positive. In this case, I made a small diagram with the colors and everything, so you can do the same too. And let's do the test then with a small test circuit. The test circuit is as follows: a 5-volt power supply, a connection to the hall sensor, an LED, and a resistor so that our LED does not burn out. What are we going to do? Power with 5 volts these points. Here I have a power supply to a transformer, which will reduce it to 12 volts. Those 12 volts, then, will enter a rectifier bridge. They will be rectified and produce 16 volts. And from those 16, I will power a 7805, which is the one that will create the 5 volts to power the hall sensor. So, here I have the 7805 powered with 16 volts in direct current, and at the output I have 5 volts. And at the output I connect the hall effect sensor. We will do the following. Through one of the terminals that will go directly to the fan, to the hall sensor, we will connect the positive. So, we connect this directly to the positive of the hall sensor, which is yellow. On the other hand, we will have a negative, which will be a more common point that will close the circuit with the LED and towards the fan. And on the other hand, we will have one of the 3 cables that will go directly to the resistor and the LED to close the circuit, but this will be connected to the signal, so that each time the hall sensor sends a positive pulse, this goes directly to the LED and can close that circuit and turn it on. Let's do that test. Let's run the board. We won't need it anymore to do this test. And here we have the LED. Well, let's energize the circuit, always with safety glasses, some fuse for any problem that may arise. And we energize. Well, here, as you can see, the LED turns on and off as the fan rotates. There you can see it. We turn off the lights so you can see it better. Well, this indicates that the sensor is working correctly. Of course, when it's going fast, we actually can't observe it, because it's a very fast flicker, but the board, the microprocessor, understands that pulse. So, what do we have to keep in mind? The very important detail to keep in mind is that not all fans are exactly compatible. It may happen that we replace a fan and it is not compatible with the original electronic board, because some very specific models, for example some Samsung models, send more pulses per turn. So to speak, the board doesn't understand the fan, doesn't understand that it's spinning so fast, and it will mark an error. Keep in mind that this can happen. But most are quite similar. They have 3 pulses per turn. Another very important detail, if the hall sensor is not working, the electronic board will turn on the fan at full speed and then cut off and mark a fan error because it does not detect the return pulse. These are very important details. Having understood this, we can now end this video about AC fans. Well, another way we have to measure the Hall effect sensor is through an oscilloscope. If we connect the oscilloscope, it will give us on the screen the pulse that is also feeding the LED. We can also see it on the screen. This is in case we want to make the measurement with the electronic board connected to the equipment. In fact, it is a pulse that is actually very fast. But what we can always do with oscilloscopes is zoom in a little on the screen. There we will see the pulse in detail, as we can see it now. This is also a method that we can use. Remember that the oscilloscope is useful for all of this. Remember that it is a 5-volt voltage, but resulting after having consumed some voltage through the magnet. That is why we always have a little less, for example 2.7 or 3 volts. And this is the power that is giving us to our LED. This is another way we have to measure the Hall effect sensor. From now on, we will be talking about the other type of fans or fan that inverter equipment has. Up to this point, we had analyzed very well how an AC fan works in an air conditioner, but in inverter we now have different fan models, such as the DC fan and also the latest model that is UVW. In reality, its operation is the same as a DC, but I name it UVW to be able to distinguish it. Finally, we have one more model, which we will later explain, that is a combination of two. So now we are going to move on to the DC blower. The big difference with this fan compared to a common one is that they are 3-phase current fans. They work exactly the same as an inverter compressor. As you can see, they have a large electronic board inside. They are completely computerized. Their connections to the electronic board also imply having some communication signal between the electronic board and the fan. These fans can be found in both the indoor and outdoor units. The one we are looking at is a typical example of a fan in an indoor unit. As you can see, it has 5 connection cables. On the one hand, it brings, on one side we have a red cable. On the other hand, we have a black cable. On the other hand, we have a white, yellow, and blue one. Each one fulfills a different function, and we will explain it to understand its operation and also to be able to make the corresponding measurements, of course. One detail that you have to keep in mind and get your mind around is that these fans are 3-phase. That is, if you look inside the fan, you will find 3 points that will say U, V, and W. This is where the fan coils are connected. Pay attention to this detail. Externally, we do not have access to the 3 coils. We can only access them once we open the fan, once we remove the rear protection, and then we can already access the U, V, and W terminals. From the cables that connect to the board, we do not have access to those coils. Who feeds those 3 coils? Well, those 3 coils are fed directly by the IPM that the fan has. The IPM is the one that, after transforming the direct current into 3-phase current, makes this fan work. As you already know, when we talk about inverter compressors, the operation is exactly the same. It is an IPM with 6 IGBTs or passkeys that are powered by 15 volts and that make the fan rotate at the speed it wants. Of course, it will always receive a notice from the board to know at what speed it has to rotate. Let's go to that. We look at this image. We will go through one by one what is the function of these cables. In the diagram, of course, we have it, but well, we are going to explain it so that it is much clearer. The black cable is always negative. It is the negative power of this fan. The red cable is the positive power of 310 volts, in case you have 220. If not, it will be 155 in case you have 110. The white cable, well, we don't have white color, we'll draw it in gray. In fact, we have it, but it wouldn't be seen. We'll put it gray to be able to identify it and understand it. It is a direct current voltage, also positive, but of 15 volts. It is the voltage that the electronic board of the fan and the IGBTs need to be able to activate. The yellow cable is also a pulse in direct current, but that goes from the board to the fan. It is a 2.5-volt pulse that the board sends to the fan to inform at what speed it has to rotate. And finally, the blue cable is also a pulse in direct current, but the other way around, from the fan to the board. But this pulse oscillates between 14 and 17 volts. So, to understand it again, fan power supply. With the red cable, all the necessary direct current voltage is sent to power the fan directly, 310 volt, 255 or 180, depending on its voltage. This comes directly from the filter capacitor on the board. Black is the negative, which is shared for all positives. White is a power supply that the electronic board gives to the fan of 15 volts that comes out after the switched power supply. With this 15-volt voltage, the fan board can be powered and also the IGBTs to be able to activate them and create the three-phase current for the fan to rotate. Yellow is communication from the board to the fan through an average of 2.5 volts. And blue, on the other hand, from the fan to the board, is informing a kind of Hall effect to inform at what speed it is rotating. This oscillates between 14 and 17 volts. Understanding all these parameters is how we will be doing the corresponding tests. Of course, as always, the first test we will do will be without voltage. The first test will be to measure the resistance between different points, and that is what we are going to teach now. Let's go to another image. Very well, here we have it. If we want to check the operation of this fan in resistance mode without energizing, obviously with the fan outside, what we will do is measure between black and red in the first instance. The resistance that should give us is approximately 20 megohms. Very high resistance. Another measurement we can do at that point when making the measurement without voltage is to measure in diode position. This is another measurement we can do. If we measure in diode position, the approximate value that it will give us will be a voltage drop of 1.2 volts to one side and to the other side. Oh well. Why does it give us this value? Well, remember that directly from these 2 points to the fan we are entering an IPM. And you remember how the IPM works. Let's see it again. You know that the IPM had, on the input side, that we talked about a positive and a negative. Look, that we always find a diode and another diode, a diode and another diode, and a diode and another diode. So, if I inject electrons from here with the multimeter in diode position, and I exit from here, the electrons will be able to pass through these diodes with a voltage drop, but towards this side they will be able to pass. So, from one side injecting electrons from here will mark me approximately 1.2 volts of voltage drop, which is the sum of two diodes, because it has to go through one and then has to go through the other. But on the other side, looked at in reverse, it will mark us OL, because we have the two diodes in reverse. So, injecting electrons from the positive, they have to pass and a voltage drop has to occur. Injecting electrons from the negative, nothing has to happen. Let's see a video in which I am doing that measurement. Now we can see the fan, we can see it well. This model is from LG. And we can see its label on which it clearly tells us what we were seeing a moment ago. And we are going to do that measurement in diode position. We inject electrons through the red positive and we have a voltage drop of 1.185 volts. With the black multimeter, I inject electrons, and I inject them through the red of the fan, which is the positive, but if I invert the cables, what happens? I have to have OL, and it is perfect. The IPM is in good condition, at least as measured from the outside. So, that is another measurement that I can do on these fans, in diode position and in resistance position, at least between red and black. Very well, now to be able to measure the following points. For example, black and white, at that point, so that you have a reference, the resistance will be approximately of 40 kiloohms. We always take black as a reference, black to white. And now we are going to go from black to yellow. And at this point the resistance will also be high, 200 kiloohms. And finally, between black and blue, and the resistance here will also be much higher because it is an internal sensor, approximately 50 megohms. So, see that from black to red the resistance is high, from black to white also, from black to yellow also, and from black to blue also. In the case of finding values much lower than these that we are going to take as a reference, we could say that some part of the circuit is short-circuited or is in poor condition. These are measurements that we will make from outside the fan. Measurements without voltage are measurements to which you can access with the fan in hand. But of course, there are more measurements to be made, and the other measurements are already on the electronic board and even with the equipment completely energized. In fact, to avoid going around in circles, you have to detect the values, the voltages that indicate here. These are the voltages that you have to be able to measure when the fan is placed on the board in the corresponding socket. We can see a socket on the board of those fans. So, having understood how the fan works on the outside, we are going to mention the following. If we see that it is damaged or any of these numbers or values is wrong, any of these components could be the problem. We can have problems with the IPM. We can have problems with some of the internal low voltage resistors, some of the SMD capacitors. Any of these components could be the problem. My recommendation is not to repair these fans, because when we disassemble them, we usually give them a small blow to the bearings and they never work well. If you detect a failure from outside the fan, I recommend direct replacement. Of course, sometimes you may want to repair and there is no problem. In the folder of manuals and diagrams that we will send you, you will find a Word file that says links to YouTube videos that are videos that I myself saw in which some people make different repairs. For example, there is a video in which the IPM of this fan is replaced. Finally, it is left with a small noise from the fan precisely because of disassembling it and touching it. But well, it can be done. The spare parts are available and it will depend on you. For the cost of the complete fan and the risks, I recommend not to do it, but well, you can see it. Well, an important detail to keep in mind when replacing these fans or looking for a replacement are the following. A very important detail is to see that the voltage is compatible. In this case we have one of 310 volts because in my area I have 220. Another important point is the power in watts. You have to keep in mind that it is as similar as possible. Of course, the revolutions are a detail that previously in conventional equipment we did not take into account, but now that everything is electronic, we have to pay attention to them. And the direction of rotation. In the case of internal fans, we will not take into account the direction of rotation because it is always the same, but external fans do. The direction of rotation goes according to the plastic blade. So, Keep in mind that it is for the same direction. So, quickly said, voltage power revolutions direction of rotation technical data sheet. Another important detail that you should not forget is the length of the shaft. Well, in fact, if the length of the shaft does not match, you will realize it over time. It is a detail to keep in mind when going to buy and to avoid unpleasant surprises. Afterwards, I recommend measuring the length of the shaft to be exactly the same as the original fan. Of course, all this in case you are going to buy a replacement and you do not find exactly the original one that the equipment had. Well, very well. Here we have with us an LG board that has a power supply to a DC fan. In the connection socket, we see that there are 7 pins, of which the first is the positive power of 220, then there are 2 blank spaces, and then follows negative 15 volts and the 2 signals. We are going to see then a little of the circuits to understand how they are powered. We always have to go back to tracing the tracks to always orient ourselves in the different areas of the board. We are going to use a multimeter tip to be able to mark. Let's see that here we have line and neutral. With line we cross the fuse. We follow the line. We cross a coil. We follow the track with the neutral. We cross another low-pass filter. Here we have the 2 capacitors. Here the 2 filter capacitors, and coils. We continue the route, and what we are going to find is the AC rectifier bridge, AC, DC, DC. Here we have a continuous, positive, and here we cross the 5th diode. And here we have the negative. Both will follow their path to this point. Here we have negative and here positive. Evidently, this large connection at this point is the filter capacitor, larger than the normal ones. Remember that this internal board also has to power a fan through the filter capacitor, so the filter capacitor will be larger than the normal boards. We have a 100 microfarad capacitor. Excellent. From the negative, of course, we will be powering, if we follow the tracks down, the switch, and then we will reach the transformer, which is this one. But also, from those 310, we have to go out to the fan. Here we have the negative of the fan, and from the positive also, here we are going to cross a small inductance, the small filter coil, and we reach the positive of the fan. This shows us that when the board is energized and receives the rectified voltage, it powers the switched mode power supply and powers the capacitor. The 310 to the fan automatically appear. These 310 volts, when we make a measurement with the entire equipment running and measure at these points, between positive and negative, we will find 310 always, whether or not the board is turned on, whether or not the fan is turned on. Better said, the board is on, what is not on is the air conditioner, but those 310 volts enter the fan. But the fan still doesn't work because it first needs 15 volts to power its electronic circuit and then enable the IGBTs. So let's get to that. Those 15 volts that the fan will receive through this point and this, they are received only when the fan turns on. And how does it do that? Through an optocoupler. The processor informs the optocoupler that it has to turn on and activate the 15 volts to enable the fan. That will only happen when it needs to turn on, that is, when I turn on the equipment. At that moment it will turn on and the 15 volts will be injected into it. This point, which was the information that the microprocessor has to give to the fan to tell it how much it has to turn, will also be given through an optocoupler. And this third point, which is the information that comes from the fan to the microprocessor, will also be given through an optocoupler. Always to keep the zones separate. Of course, a fan can be damaged, short-circuited, or exposed to more dust. We don't want that to affect the microprocessor. That's why optocouplers are used. If you look closely, there are two that have to inform from the micro to the fan, to activate the 15 and to inform how much it has to turn. And there's one that has to inform from the fan to the micro. That's why you're seeing that they are placed in two different positions. There are two on one side and one on the other. 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3. For maybe if we see them from the other side, you will be able to understand them better. You already know where the point of the LED is. Here we have one and here another towards the fan, and here we have one from the fan. We have it marked on the board. Of course, any damage to these optocouplers or the components that surround them, which are all of these, any damage to any of these resistors, capacitors, jumpers, or transistors, which we will be learning how to solder, know its value and replace, any damage to these affects the operation of the fan. Pay attention to that detail. And one more detail, if the switched mode power supply, here we have the switch and here we have the transformer. If 15 volts are not generated from this side for it to work and activate the fan, well, we will not have the 15 volts for that. IGBT then will not work either. So any damage in this area, the fan stops working. That's why, check all of these components very carefully and, of course, follow the tracks. You will see that the tracks are very fine, and believe me, many problems are due to burned or damaged tracks. Well, this is how a fan is energized. Keeping all this in mind, later we will test the voltage with the equipment running and, at that point, you will deduce if the problem is the board or the fan. What is often what we want to know. Or maybe we have a problem in the fan, but we also want to see that the problem is not the board. You also have to know how to understand everything we explain for the measurements we are going to make. Now we are going to talk about the third type of fan that we will find in inverter air conditioners. I call this type of fan U, V, W, because it has three wires, U, V, W. It works the same as the previous one, but the big difference in this one is that only the three-phase coils are located inside the fan. The IPM and all the circuit that controls it is located on the electronic board. Understanding this, there are two details that you will have to keep in mind. In this case, it is located on the external board, outdoor unit, as the external board controls all the details of this fan, speed, rotation, power consumption. It is essential that when you replace this fan it is exactly the same. Attention, that detail has to be exactly the same because the board controls everything. So, any data that the board finds wrong will already mark an error. We are talking about voltage, power, amperage, rotation, and, of course, direction of rotation. It has to be exactly the same. When replacing, we have to get the same model. Another disadvantage of this fan is that when we place a universal inverter board, we will explain how to do this later. We cannot adapt this fan to universal boards. We have to change the fan. This does not adapt to universal boards. Another disadvantage, which I will explain better later. So, how do you measure these fans to see if they are good or bad? It is done only in resistance mode, and the resistance has to be exactly the same in all points, 97 ohms, 97 ohms, and 97 ohms. The resistance has to be the same. It is a three-phase motor. Its phases will be run in time thanks to the IPM. So the coils have to have the same resistance between them. Please observe on the board the IPM of these fans. Here we are seeing a Carrier or Myers board. In Mexico it is known as Myers, and in Argentina or other countries it is the Carrier model. And in many other countries this is the same as Medea. In fact, the electronic boards are Medea brand. Whenever a board says KFR, we are talking about Medea boards. Well, this is the IPM of the fan. This one we have here is the IPM of the fan. You will identify it because on the board you will find a heatsink further away from the main heatsink. Sometimes the IPM of the fan can be next to the IPM of the motor. They tend to be together using the same heatsink. In the case of this board, no. So, what does the Teams microprocessor do? The microprocessor is the one that tells it how fast it has to turn. Through these tracks that we can see here, the microprocessor tells it how fast it has to turn. When we get closer, we can see the tracks. And the IPM also informs it at what speed it is turning and what consumption it is having. There is constant communication between the fan control device and the microprocessor. We will also find the capacitors that maintain the 15 volts of the IPM and nothing else. After that, the only thing we have is the connector that connects the fan and the U, V, W terminals. So, the entire control circuit is directly on the external board. The measurements that you can make are many. Anyway, you know how IPMs work. You just need to know which is the 310 input and the U, V, W output to be able to make the measurements that you already learned in the compressor classes and the three-phase motor class. Exactly the same as to measure all the parameters of an inverter motor. What else can you measure? The capacitors that maintain the 15 volts. And also, please do not forget the communication tracks. They are tracks that we can barely see at first glance. Use a magnifying glass, use a microscope and observe that no track is cut. Because many times the problem is that sometimes we take the board to an electronic technician and we only see that he connected a small cable and the board already works. Because the tracks are often cut. So don't neglect that detail. Don't think that it can't be damaged. The tracks are damaged very often, please check that. Those are the details of a U, V, W compressor. To keep in mind that we have these fans, we will see some photos. There is another photo of U, V, W. They are very solid, very robust, they are heavy. They have permanent magnets inside. They have good rubber pads to hold them. We can observe it here. And the speed measurement, remember that it is produced through the loose cable. The loose cable produces a voltage drop. The one of the three that remains free produces a voltage drop which informs through the IPM to the processor the direction of rotation, better said, the speed of rotation. So it's like they have an embedded Hall sensor, just as we talked about with inverter compressors. But we have one more model of fans that is similar to this one, and I will go on to explain. As I said before, you will find a certain inverter fan, U, V, W. But what you will also find, here comes a three-phase current created by an IPM, but within this, you can also find one with 6 cables, which has 3 power cables and 3 Hall effect sensor cables. Keep in mind that you can also find these fans, but with 6 cables, since their electronic computer does not have the ability to detect the rotation through the loose coil. So, what do they place? A Hall sensor to be able to make that rotation measurement. Keep in mind that you can find it like this. If you find this format, the Hall sensor measurement is the same as we explained in the previous videos. It is powered and it is seen if there is a return pulse. And the coils, of course, are controlled exactly the same. In this case, the IPM is inside the electronic board. Well, know that this model of fans also exists that you may find at some point. To continue our training, we are going to be changing modules at this time, and we are going to talk about electronic expansion valves. I don't know if you have already come across these valves, but so that you can recognize them visually, they are like this. They are not only solenoid valves that open and close, but they are expansion valves that are constantly varying the flow of refrigerant that they let pass through. So, the errors they present, the measurements we are going to make, how they work, we are going to be analyzing it now. For those who still don't know, they didn't realize, this expansion valve replaces the capillary in conventional equipment. In inverters as well, more conventional or of lower quality, there is still capillary, but in the best ones we already have expansion valves, such as in Carrier or Myers. How does this valve work? Well, but in you who have 6 connection cables to the board, these 6 connection cables are basically as follows. Look, we have 2 cables that are negative 12 volts, and then what we have are 4 more cables that are going to be injecting the positives, and with that they are going to be closing the circuit in the coils. One moment, I'll find you a diagram with which we will understand it perfectly. Basically, they are 4 coils. They are 4 coils that are energized with 12 volts through pulses, and they are going to close circuits. For example, we will be injecting electricity through the brown and red. And when we want to rotate each of these coils, the board will give pulses to the white cable, the orange cable, the blue cable, or the yellow cable. As it gives pulses, it is causing electrons to circulate through one after the other, and after the other. It works like a small stepper motor. It works exactly the same as the air oscillating motors of the previous unit. Do you remember this air oscillating motor? In the same way these expansion valves work, allowing the board to control the exact position in which the rotor is located. These usually had 5, and this is because one of the 2 was shared. Red was also brown. Red and brown were together, which would be the same in the end. But in the valve to have more control yet, it has 1 more, that is 6. How do we understand its operation? Understand that it does it through pulses. That is, the board does not send a constant 12-volt signal, it sends pulses. And when it sends pulses, it makes the motor go around, very fast pulses. That is why, if we inject 12 volts directly and fluids and clean, it may be that this component burns out. If the valve does not work, the first thing we will do is test the electrical or electronic part, which is composed, obviously, of the wires and also of the winding that is placed on the top. If you look closely, it has a way to turn and remove, very similar to how we removed the coil of the hot-cold valve of the 4-way valve. It is removed and we can remove the electrical or electronic part. This electrical or electronic part has a simple measurement that we can do, and it is through ohms. If we control and measure, for example, between white and red, obviously we are measuring the winding of this coil. Then between white and red it will give us a result of 43 ohms. These ohm results are similar in all valves. They are not exactly like that, but they are very similar. Now, if I control between yellow and blue, look that I am traveling 2 coils. In that case, between yellow and blue, the resistance will be double, 85 ohms. And so with all, between orange and red, between brown and blue, between brown and yellow, and between orange and white. To measure double, in all measurements, I will have to have results like these that will be given by the number of coils that I am controlling. Well, this is the main way to be able to measure it, and it is an electrical/electronic way without voltage. Let's watch a short video where it shows us the measurement we did. Here we are seeing how we do that measurement. Look, we have 90.8 or 9 ohms. In another one, there are 45.6 ohms in one of the coils. There is nothing there. We also have to control between the ones that are opposite to know that we do not have any false measurement. That is, the coils may also be short-circuited, so we have to measure between the ones that are separated to see that the travel is open line. In the next measurement, we have another coil. And that's how we keep going through all of them. I am letting you know that the link to these files is in the video description so you can download them. You saw that the values will be approximate. A moment ago, in the measurement we made on that carrier valve, we were talking about having 90 at this point, and here we had 45, approximate to this example. Very well, this with respect to the electrical/electronic part of the expansion valve. But, do we have another part in the valve? Yes, we have the mechanical part that lets in and out the refrigerant, and that is where we have to be more careful, or rather, it is the most complicated to repair, because to replace that valve you have to solder and unsolder. So, let's say that we have a problem or a defect in the mechanical part of that valve, that is, the part that allows the refrigerant to enter and exit. How are we going to detect the problem? Since the equipment will not mark us an error of electronic expansion valve. We will not have that error in the equipment. In reality, detecting this error in an inverter unit depends 100% on your knowledge and understanding of how a unit works. Think that if this valve is staying closed too much, the internal and external pressures will vary, as well as the discharge temperatures of the compressor and the equipment will mark an error, for example, excessive overheating, excessive supercooling, excess compressor discharge temperature. They are rare errors that usually have to do with the refrigerant, up to lack of refrigerant. All of these errors can be indicating a defective expansion valve. Of course, this depends solely and exclusively on us to be able to detect that error. Some errors are excessive overheating, excessive supercooling, excessive compressor temperature, and lack of refrigerant. They are errors if the valve opens or closes too much. But we have a way to test the electronic part of the valve. It would be to disassemble and remove this part of the valve, the electrical part. And inside it, we can place a screwdriver. When placing a screwdriver and allowing the valve to activate by turning on the motor, or with a universal board, that screwdriver will move because it will stick to the different walls of the valve. This is an electronic or electrical way to test it. Energizing the valve, we place the screwdriver inside and it has to stick to the edges. Now, if we see that the entire electrical part works well but still has an error, temperature, or strange pressure, well, it is time to think that the problem may be here, in the mechanical part. A quick way to see if this turn works or not is when we energize inverter units. In general, the valve makes a complete opening and closes again. So, at the time of energizing, we have to hear the noise of the electronic valve rotating, which would indicate that it is in good condition. We have to hear the noise of the opening and closing. It sounds like a knocking noise, something like that to understand it. If we still notice that there are defects, something that we can do in some cases, it works in others, is with a magnet, with a strong magnet, perhaps those that are used to recover fallen screws. Without the electronic part in place, with that magnet, move it around the valve and see if the valve rotates, activates, or does anything. Move it around the valve to see what happens. Because it is very sensitive to the small magnetization, it rotates or moves. So you have to move it around and see what happens. Sometimes it can open a little and see how the refrigerant pressures vary. Now, if all this still does not work, well, we have to be thinking of replacing the electronic expansion valve. In that case, what we will be doing is applying the following tips. You saw that the valve has the electronic part and the welded part. And you will see here that the space from the weld to the valve is very short. What is the problem? The problem is that in order to solder this valve, we have to completely wrap it, of course, without the electronic part connected because we are going to remove it, but the mechanical part we have to wrap completely with a damp cloth so that it does not overheat. That damp cloth must be made of cotton and be constantly wet. In fact, if you have an assistant who is sprinkling water on it while you are soldering at these points. The problem is that the position of the valve is always like this, standing, and when you wrap it with the cloth, it drips and cools the weld, which makes it take longer to solder and the heat reaches the valve and can damage it. A tip from me is, originally we have it in this position, and at this point we have to solder. And here the air conditioner continues. These pipes will continue and will go around below and go to different parts of the piping. What can you do instead of soldering at these points? Well, when you buy the expansion valve, you can place it on its side where you can wrap it better with a cloth with water and solder some longer pipe sections, and leave your expansion valve with longer pipe sections. So, what will you achieve? Well, when you are going to place it in the equipment, the welding you will do on the equipment will already be much lower, because you will cut the pipes here, because your expansion valve already has longer sections in place. Unfortunately, they come with very short pipes that make it quite difficult for us, but if you take the time to add these sections, you will surely find it much easier to solder because you will be able to wrap it with a damp cloth without problem, and you will be away from the welding area, which is this. A very important detail is that all this is always welded with an atmosphere of extra dry nitrogen. I don't know if you know or not what this is, but all this has to be welded with a certain amount of nitrogen passing through the pipe constantly to prevent the formation of the common slag when we weld. When we weld a pipe, what always happens is that at the weld point, we clearly see that a certain slag or residues are formed that are the fault of the burning of oxygen together with moisture. The same thing happens inside. Now, By sending a constant atmosphere of extra dry nitrogen during welding, we prevent the formation of that slag inside. And so we have a clean weld inside, which then, when the refrigerant is circulating, will not drag those residues inside and clog another component, such as the expansion valve itself. So, always with the atmosphere of extra dry nitrogen. Later, I might leave a video explaining this. It is not necessary to explain it in inverter refrigeration because it is not specifically about inverter refrigeration. In reality, it always had to be like this, but in inverter it is more than necessary because we have equipment with 410, with 32 which are more delicate gases, of which we have to be careful of all those residues that remain inside the pipe. Well, this is what has to do with electronic expansion valves. I will briefly show on the board how this valve is connected. Here we have a board with a slot for the expansion valve. In fact, it doesn't have the slot, it just has the slot because this model didn't come with it, but look at the following. In this point, we have an electronic expansion valve, which connects to these 6 terminals. And these 6 terminals go to a driver, which is a series of electronic valves that act as communication between the processor and the valve. That is, the processor does not directly control the 12 volts of the valve, but does so through a driver, a series of pass valves. We can say that it is something like a small IPM. And they give the valve pulses as they want. There are several electronic pass valves that allow the 12 volts to pass directly, commanded by a much lower voltage that comes from the microprocessor. In this model we do not have it installed because this model does not have it, so neither the socket to connect the valve nor the driver is installed. But that's how it's controlled. We could measure the pulse emitted by the board with an oscilloscope in case it were the board that brings it, but well, this area does not usually fail. Most of the failures are in the valve itself. And one more detail to keep in mind that I mentioned, and then we will see. To be able to control an expansion valve correctly, you will need a universal board. With a universal board, we also have the possibility of testing electronic expansion valves. So that's where we get to the topic of expansion valves. Next, we will continue talking in this part of the course about temperature sensors. We will be seeing many details about the sensors, their resistance values. We will be understanding how they work in a conventional and inverter system. We will also be understanding how an electronic board can make these be part of the electronic circuit. That is, part of the electronic board influences the operation of temperature sensors. Something that can be damaged in this system is not only the sensors, but also the circuit involved in temperature measurement inside the electronic board. So we will explain all that, but to start we will be seeing or understanding how these temperature sensors work. It is key to understand how they work, and that is what I will apply. These temperature sensors are NTC. That is, their temperature coefficient is negative. What does it mean? That it is exactly the opposite of its operation in resistance. To understand it better, we will make a small graph in which the variable below is the temperature in degrees Celsius, and the vertical variable is the resistance in ohms. As the temperature increases, the resistance decreases. These temperature sensors are small NTC ceramics because their reaction to temperature is to reduce resistance. It has been reached as a kind of agreement between manufacturers, and it has been said that to name a sensor, we will say what value of resistance it maintains at 25 degrees Celsius. To name a certain sensor, we will use as a reference its resistance value at 25 degrees Celsius. So you are finding, for example, 10 kilo ohm sensors on the market. What does it mean? That at 25 degrees, that sensor has a resistance of 10 kilo ohms. What do we mean by resistance? I will do a small measurement to understand and know what it is about. For those who have never done it, we grab the multimeter, put it in resistance position, and simply measure the sensor uninstalled from the electronic board. Well, here we have a 10K sensor. Why do 8K appear at this point? Because evidently we have a temperature greater than 25 degrees here. As its coefficient with the temperature is negative, this sensor evidently, as all sensors, has a graph that looks like this, and we will have 8 kilo ohms when the temperature is a little higher. In this place, it should be about 28 degrees Celsius now, so we have 8K of resistance. Remember the word NTC. This will help us understand that if we increase the temperature, the resistance decreases. It is negative, it is the opposite. Now, PTCs are different. This is only for informational purposes. It is not relevant in the case of inverters. PTCs are ceramics that are used, for example, to start refrigerator motors whose coefficient with the temperature is positive. What does this mean? As the temperature increases, the resistance increases. A PTC, for example those that are used to start refrigerators at 25 degrees, is approximately at 20 ohms. There it is, more or less you can see it. So, when the temperature increases, the resistance increases. The difference between PTCs and NTCs is that they are positive in relation to temperature, that is, they increase and continue to increase. PTCs are often used as starting devices because their line is not predictable. That is, if it heats up faster, the line will be like this. If it heats up slower, the line will be like this. And when it cools down, it will be different. The same ceramic can find in different temperatures several resistance ranges because its working line is not predictable. So it is used as a starting device. The temperature increases, the resistance increases, and the starting coil detaches, as is the case with refrigerators. NTCs are predictable, which is why they are used for precision temperature measurement, and that is why NTCs are the ones we will always find in areas where temperatures need to be measured. Okay, this is how NTC ceramic sensors work. What values do each ceramic have? We can't see it from the outside because it's actually a package. The ceramic is inside. The ceramic looks similar to the one I'm going to show in an image so you know what it looks like inside. And also see why you won't have the value on this component because this is not the sensor. The sensor is inside. Something like this is what these small ceramics look like. An important detail to keep in mind, there are many values. If a manufacturer tells us that this sensor is 10K, here he is indicating that it is 10K at 25 degrees. But you will also find them, as many already know, you will also be finding them, for example, always talking about 25 degrees. The value I say in kilo ohms or less is the reference temperature value at 25 degrees. So far you have found 5K in conventional equipment, 10K, 15K, and 20K. And in refrigerators, for example, the Whirlpool brand has a 2.7K sensor, others also use 5K. Well, what does it mean when a manufacturer or a spare parts seller tells us that this sensor is 15K? Remember that he is telling us that it maintains this value at 25 degrees. It is not that it is always 10K. In fact, we just saw it with this sensor. right now it has 8 kilo ohms of resistance because we have more than 25 degrees. It reacted to the temperature, which is fine, it is correct. Something else that we also need to understand is that we need different values of sensors depending on where we are going to place them. Let me tell you the following. When we talk about 5, 10K, the letter K represents a multiplication by 1000, so in reality this sensor is 10,000 ohms. Temperature sensors on electronic boards have high resistance values. They are not 10, 100 ohms. No, we are talking about 2,700 ohms, 5,000 or 10,000, 15,000, 20,000. Okay, this is how temperature sensors work. I will explain below their application in air conditioning systems and also in inverter systems. So, in inverter technology, we will be finding different sensor values because we have to measure temperature in different points. In an inverter unit, we will be measuring temperature at points such as the indoor ambient temperature. We found this not only in inverter, but also in conventional. I'll see if we can go down and make a small box to understand it. Indoor ambient temperature. So far we found it in conventional and in inverter. Indoor pipe temperature. As they told you, many overheating temperatures, although it is also subcooling, depending on whether the unit is hot-cold or cold. We'll just call it indoor pipe temperature. In this case, we also have it in conventional and inverter. Outdoor pipe temperature. In this case, in inverter, we will always find it. In conventional, we will find it, but we will put an asterisk. The asterisk will tell us that some will not be found in all conventional units, and I think you know this. In inverter, in addition, we will have outdoor ambient temperature. In this case, we will always find it. Sorry, I made a mistake. We will always find it in inverter. In conventional, we will no longer find it. Finally, compressor discharge temperature. This will not be found in conventional either, and will always be found in inverter. This would be a small box made quickly so that you can visualize and understand what you will find in inverter and conventional. So, when in conventional you will be finding 2 to 3 sensors, in inverter you will find 5. You will always find 5 temperature sensors. All these temperature sensors can have a similar travel value because they are handling temperatures from 4 degrees to 50, 60 approximately within all ambient temperatures. Although, of course, it does not make 60 degrees in many parts of the world, but if they are temperatures close to ambient temperature, then the values of these sensors are usually similar. For example, they usually place 5K or 10K, although some manufacturers vary the values, but approximately they are like this and they are all similar. Now I will explain why in a moment, but the compressor discharge temperature has to have a temperature sensor with a higher value. And that is why in inverter now, additionally, you will find sensors of 38K, 40, 56, or 200K. Yes, in inverter we will find one of the sensors that will have a much higher value. Why does this happen? Don't worry, we'll understand. Let's go back to the graph where we were talking about sensors and their operation. The compressor discharge temperature is a temperature that the equipment measures precisely at the compressor discharge. That is, it has the ability to measure the temperature of the compressor itself, since that sensor is so close to the outlet that the temperature in that pipe is similar or almost equal to that temperature of the compressor itself, and therefore, of the oil and the entire casing. Here we can see it. The outlet of the compressor pipe makes a small turn, and there we already have the temperature sensor. This is the sensor we are talking about. This is going to be measuring temperatures of 80 degrees and more. Why does it have to be more valuable than the rest? Well, because when it is approximately that temperature at 80 degrees Celsius, if we place a sensor of 5K, 15 or 20, it will be in a range of the temperature sensor in a resistance range that will be so low that for the plaquette that measures that temperature, or that value, in reality it measures it with a small voltage of 5 or 1.2 volts, it will be a value so low, for example, of 100 ohms, that it will not be able to understand it. So, in this place where such high values are measured, what does the manufacturer do? Well, the manufacturer places sensors that are now not 10K, but now 200. Not all of them have 200, some 38, 40, depending on the manufacturer of the plaquette, but let's say they use 200, as is the case with some very well-known brands. So, at the point where it reaches 80, 90 degrees, which is the moment when the plaquette wants to know what temperature the compressor is at, there is a value in ohms of, for example, 5 kilo ohms. It is a value in ohms that the plaquette can understand. And that serves us, the plaquette needs it. So that you understand, in places where high temperatures are measured, and I refer to high temperatures as passing quite ambient temperature, such as 80, 90 to 100 degrees, we are going to place sensors of high ohm value, because the value in ohms is always taken as a reference at 25 degrees. Now, in places where low temperatures are measured, we will have low ohms, because when the temperature drops, the resistance will go up, and it will be easier for the plaquette to understand it, such as, for example, in a freezer of certain brands such as Whirlpool. In these freezers of refrigerators we find sensors of low resistance, so that when the temperature drops and is found at a point that the plaquette wants to understand it, the value in ohms is appropriate for that electronic circuit to understand it, perhaps 15 to 20 kilo ohms, approximately. I'm going to erase this and we'll continue with our graph. This would be the case of a freezer, and at this point I'm going to find 20 kilo ohms. These electronic plaquettes always want to understand values from 3 to 20 kilo ohms. That is why, if they want to measure temperatures in places with a lot of heat, they have to put higher sensors, so that when they are in the range that matters to us, the value in ohms or travel is the appropriate one. And the same vice versa, if we want to measure very low temperatures, we put low ohms, so that when the temperature we are interested in is reached, we have the appropriate ohmage so that the plaquette can understand it. For that reason, we are going to find a sensor and inverter that will be of more resistance. But you have to learn where they are, you have to see them visually and understand how they work on the electronic board and what errors they present. And we will see that below. Okay, to understand how a temperature sensor works inside the board, we're going to use a small sample diagram. This is a simple diagram that many boards use, but there are more complex ones, and we'll be seeing some of them live soon. So, how does a temperature sensor work in a diagram? What the microprocessor, actually, the integrated circuit, will feel is a voltage variation depending on the resistance of that sensor. In the sample circuit, this represents the NTC, the thermistor or temperature sensor, or NTC variable resistance. So, As this temperature varies, the resistance varies and the resulting voltage that enters the integrated circuit is different. 5 volts positive are injected directly into the sensor, and the negative is injected. This is the GND, the negative, through a precision resistor. It is not a common resistor. And through it, a voltage of equalization is reached, and the resulting voltage goes to the integrated circuit. As a result, as this resistance varies, the voltage that enters the microprocessor also varies. If we inject 5 volts into the sensor, approximately 2.3 to 2.8 volts will be injected into that integrated circuit, and through this variation, it understands what temperature it is. Of course, it understands it in a much more accurate way, 2.340. 2.565, we talk in the range of millivolts, so the microprocessor understands it. Something that is not drawn in this diagram, which you will generally find, is a capacitor that is placed between the negative and the positive. Any error in the tracks, capacitors, or resistors in the temperature measurement circuit can cause the integrated circuit to mark a sensor error, even if the sensor is in good condition. That is why it is important to pay attention to that detail, as it may be that it shows us a temperature error or a temperature sensor error, but that the problem is not the sensor itself. That is why technicians often replace the sensor, but continue to have problems, because in reality there is another problem inside the board. Of course, for that they need to have a little knowledge of electronics to identify it and solve it. Well, this is a normal circuit. Let's see then this same thing, but on an electronic board. Let's take a look at the temperature sensor circuit on an electronic board right now. Well, let's zoom in a bit on this part of the board where we have the connection to the NTC sensors. At this point, we can already move some components that we will identify as, for example, precision resistors, and we also have a capacitor very close by. Let's turn this board over and let's see what we find on the other side or understand how this board measures temperature. We get closer and we have the following. These are the points where we have the temperature sensor placed. If you look closely, these sensors are being powered by a positive. This is the positive track. There is a capacitor between the positive and the negative. This white track is the negative. And here we have the capacitor we mentioned. Of course, it has to be in good condition for the temperature measurement through these sensors to be working properly. For the integrated circuit to understand, all of these components must be in good condition. If we continue observing a little more, you will see that we find, at the output of each sensor, precision resistors to the negative that are the ones we just saw from the other side. Of course, we have to corroborate its operation. We have to corroborate that they are exactly in the value they have according to their color bands. They are precision resistors, that's why they are green. And if we look from one end of the sensor, from the same one where the precision resistor comes out, we have some very thin tracks. They are these two, the ones for the two sensors. If we follow its path, well, towards the negative it goes back through some small lens-shaped capacitors that must not be in short circuit. We keep going. They were these two, and look that we reach 2 points of the microprocessor. This is where a resulting voltage is delivered which the microprocessor understands and can know what temperature that sensor is at. Very important detail, the microprocessor will only report a sensor error when we see an error message on the equipment's display. This only occurs when the voltage arriving at the microprocessor is 0 volts or 5 volts. Therefore, if the sensor is devalued, if the resistor is devalued, or if there is any other strange problem that is not, For example, a direct track cut, the voltage that will arrive will be strange. The microprocessor will understand that this is a temperature. For example, the microprocessor may understand that the room is 0 degrees due to an error in some value. Then, you turn on the air conditioner and the unit will not turn on, of course, because it thinks it is already cold. Therefore, pay attention to that detail. We do not absolutely trust the errors that the equipment reports. If we see a unit that does not turn on the compressor even though everything is properly configured, there may be a devaluation in the sensors, which causes the microprocessor to misunderstand the temperature. That is why that detail is important. Understand that, if 0 or 5 volts arrive here, the microprocessor will understand that there is an error. For example, a short-circuited sensor, 5 volts, sensor error. A temperature sensor, an open NTC, 0 volts, there is also another problem. Or a cut track, 0 volts, there is also a problem. The microprocessor understands that, but when there is devaluation, the microprocessor does not understand that and will not produce a strange effect, which perhaps will never blame a sensor or the circuit, and it is so the problem. So, pay attention to that detail. Therefore, remember that important data. If we have 0 or 5 volts, we will have the error. When there is an intermediate voltage, it is good, the temperature is being measured, but it may be some problem in some of the devalued components. Very well, how can we know if the components are in good condition? One way is by measuring the voltage that is emitted to the sensor. We will also do this with a powered board. But for now, you can measure the tracks, check them, measure the resistors, and the capacitors. Now we will continue with our topic of sensors. We will see a small track tracing on an electronic board of an LG inverter unit. Here we have the position of the sensors. Please observe the components that work alongside the sensor. In this case, the components are much smaller than the boards we were previously seeing. Well, you have to follow the tracks in a more delicate, patient, and attentive way to be able to observe. Observe, near the temperature sensor we have certain capacitors and resistors, and several tracks that directly lead us to the microprocessor. All of these are components to review in cases of temperature sensor error. To review these components, sometimes you will need to have some kind of magnifying glass or microscope. In this case, I am looking through the camera screen, but if I look with my own eyes, it will even be quite difficult for me. I see it better as you are seeing it through the camera. At a glance, these numbers are illegible. And through the camera, you can see that it has a resistance of 12.1 K. Well, very well, with patience, review these tracks and these temperature sensors. And we will move on to a slightly more complex board. I will show you a board from a unit, as it is commonly called, Chinese. Let's see that the location of the sensors that is at this point also has very close to those delicate components. And the peculiarity of these boards is that they are double-sided, that is, they have printed tracks on both sides. Here we can see some of those components that have a direct relationship with temperature measurement. The microprocessor is a little further away. Let's see what we have on the other side. Look, here we have a track. The tracks of the sensors that use components that are on the other side. Here is the tracking. They cross to the other side through those perforations. And on the other side, we are already almost at the microprocessor. There it is. With patience, we place the tester in continuity and follow the tracks when we have temperature sensor errors. With a lot of patience, the resolutions are achieved. And we do it this way. Very well, we will do more tests, but now measuring voltage in the sensors. We will build a board in the next video. And we will measure some of the voltages we were talking about. Now that we have this board energized, let's test the voltage on the temperature sensors. We will put the multimeter in direct current reading, and we will measure the different points of sensor energization. Let's try. Here we have 5 volts. It is not clear due to the reflection of the light. Let's wait a bit. Now yes, 5 volts. Well, we are powering the sensors with 5 volts. Let's see if this other one also powers with 5 volts. Let's connect the temperature sensor and see what happens to that voltage. Two volts almost, yes, because it is quite hot here, but if we cool it down, if we could lower the temperature, we will see how that voltage increases. Let's heat it up a bit to see how the voltage varies. There it is. I'm heating it up. We are seeing how that voltage drops significantly. If we place a temperature sensor of a resistance that does not correspond, in general we will have very strange voltages. If we place temperature sensors that do not correspond to the resistance that the manufacturer has put on the board, in general the results here will be 0.5 or 4.5 volts. Since we have the correct sensor, the resulting voltage of the 5 volts that are emitted when we connect the sensor, our resulting voltage is between 1.5 and 4. That tells us that we are placing the correct sensor and that it is working well. Voltages of 0.5 or voltages of 4.5 already indicate a devalued sensor or that it is not of the capacity that corresponds to that electronic board. Keep in mind that we can do the same measurement and control which sensor goes in each unit. A detail that I also think you need to keep in mind is that not only do the boards energize the sensors with 5 volts, we have electronic boards that energize with 1.2 volts, the ones that are a bit more computerized, such as the case of the other board that we have as a model here. These electronic boards energize the sensors with a much lower voltage, approximately 1.2 volts. The resulting voltage when connecting the sensor is approximately 0.3 to 1 volt. If we find values very close to 0 or very close to the voltage without the sensor connected, then it may be that we are talking about some error or a sensor that does not correspond to that equipment. Very good. This measurement that we will be doing to see if the circuit on the board is working properly, but this measurement is already with voltage. In this video, we will be talking about the remote control and also the receiver of the same on an electronic board. The remote control works in a very similar way to an optocoupler. An optocoupler has a small LED and a small photodetector inside it. In this case, it is exactly the same, only that the LED is in our hand and the photodetector is located on the electronic board or on the display, or on a small separate board. In this case, we have it together with the display. How does it send the signal? Well, it does it through pulses. These pulses are very fast in time and we only see a light if we look with the camera of a phone, for example how we are going to see now pointing with a phone. And there we can see a slight blinking. Well, let's try with another different control. There we can see just the blinking. This blinking is telling us that the remote control is working properly. In case it is damaged, what we can do is replace this LED. In reality, what breaks the most in remote controls is this LED due to falls. It is rare that it fails for anything other than falls, unless water or dirt gets into it. If you observe inside the control, this LED usually has long wires to connect it to the board. This is to cushion the blows that these devices constantly have. But they also get damaged sometimes. So, we have to replace it. In case this LED fails, it is easily replaced by another infrared LED. But it is not only the only failure we have in remote control and its reception. It is also possible that we have a failure in the receiver of this control. One detail I want to mention is that iPhone phone cameras do not show infrared light. These phones are made in a way that the screen does not show the spectrum that is invisible to the human eye. In this way, they offer a better image quality. Therefore, let's keep that detail in mind. With iPhone phones, we will not be able to see the light of the remote control. We may think that the control is having problems, but it is not because those phones do not show that light spectrum. So, how do we control the receiver? One simple way to do this is to go to the 7805 on the board or to the 5-volt output and make continuity between the negative and any of the 3 pins of the receiver. There it is. There we were able to identify that the middle one appears less than 1 ohm. So, that is the negative power supply of the receiver. In case we have to replace it, we have to look for one of the same type. The main thing is that the terminals match, because if not, we have to make a great adaptation on the board. The main thing is that the terminals match, both the negative and its BCC power supply and its signal output. To see the BCC power supply, what we are going to do is place it on the positive side of the output of the 7805 and also make continuity. It will not be a direct continuity, but it will be a low resistance. Here we have 329 ohms. Here we can identify the input power of this receiver, and on the other side we have the signal output. So, how are we going to do to control its state? We are going to power the receiver along with the entire board. So, to control the operation of the receiver of this control, the first thing we will do, as we saw in the previous video, is to corroborate which is the negative and which is the positive of the sensor. And we were able to identify that already. Next, with the oscilloscope, we will detect between the negative and the output. So, we turn on the oscilloscope, place the test lead in 1x, also informed that we will work with 1x, and only need to set 5 volts, or we can even use 2 volts, since on screen we will have 8 on each side. Then, we place the positive on the signal output and the negative. We will place this one on the negative. Remember that the right one was the positive. Now I am placing it on the left, which is the signal output, and the negative we will place it on the negative, but for that we will take advantage of the other side of the sensor. Very well, carefully not to short circuit. As we see on the screen of the oscilloscope, we see a voltage of 5 volts. This voltage must vary as we illuminate that receiver with any remote control. It doesn't matter if it's not from the air conditioner, all signals are received and transmitted, but not all signals are understood by the microprocessor. So we press the volume button on a TV. The TV volume button gives a constant pulse that, in general, air conditioner keys do not give, since they prefer that we press them one at a time. The TV volume always gives a constant light emission, and there we can see how that pulse is drawn. Let's zoom out and we can see better. There it is, there we can see the pulse. Let's give it less zoom. And see that we can see how it is being drawn. I don't press, I pressed, I hold down, I let go. Now I'm going to press the power button. And the signal is always being received. Depending on what we ask the team, they are not always understood. For example, in this case, the team is showing an error, so even though I raise and lower the temperature, the team does not react and does not raise and lower the temperature. But the receiver of the remote control is receiving the signal. In fact, even if I press the power button on my TV, the signal is still received, and the receiver transmits it to the microprocessor, but the microprocessor does not understand it. But this tells us that the receiver is working well. Remember, between G and D, or negative and S, there the voltage already fell because I disconnected it. So this is how we can test both the remote control and the receiver. Very well, to continue with our training, we are going to touch on a very interesting topic in inverter technology, which is the bidirectional communication signal between indoor and outdoor units. It is a very interesting topic because, in addition to being damaged quite a bit, it is a complex topic for most technicians. It is difficult for them to understand it really, but we are going to give explanations as always simple, clear and sharp so that you can perfectly understand how these communication signal circuits work. As a sample and to be able to explain it and understand it, we have an indoor and an outdoor plaque with its reactor, which it needs to be able to turn on and energize. Here we have the electrical interconnection, line, neutral, and signal. They are the only three cables we have. We don't have the earth placed so as not to confuse us, nor do we even have the display placed. To understand how this works, first of all we are going to do some measurements and then we are going to be explaining in graphs how it works, what it does to be able to communicate from one side to the other. The first thing you will do, when repairing or checking inverter air conditioners, when you have a communication error, is to energize the indoor or outdoor unit, the one that is energized, and to be doing some measurements on the communication cable. How do we do it? With a simple multimeter. We place the multimeter in direct current and measure between the N cable and the S cable, and we will observe what appears on the screen. Preferably, place the black cable in N and the red cable in S or C of communication. Well, now we don't have any voltage. It would be perfect. Let's start the team. Now yes, we have to find the voltages that interest us. Observe, please hear the number I have on the multimeter, 15 volts, 4, 22, 15. 2, 22, 15. 4, 22, 15. 2, 20, 15. 4, 22, 15. That data is important. That variation is important. Do you notice that there is an intermediate voltage? 15 goes down and goes up. It goes to 2, it goes to 22, to 2 and to 22, and goes back to 15. That's how an indoor unit communicates with an outdoor unit. When the voltage drops, one communicates with the other, and when the voltage rises, the other communicates with the first. That's the way they have to communicate with each other. That's exactly what we're going to see with the oscilloscope. There are units that communicate up to 50 volts, so we have to activate 10x. Tell the multimeter that we're going to use 10x and place the negative test lead on N and the positive lead, or the positive test tip on S. We're going to zoom out so we can see what's on the screen. We'll increase the voltage a bit so that 40 volts appear on the screen. Okay, there we have the same thing we saw with the multimeter. It stays at 15, goes down to almost 0, to 22, 24, and goes back to 15, 0, 22, 24, 15, 0, 24, 15. And it's about every 3 or 4 seconds that the communication takes place. Approximately every 3 or 4 seconds, the units communicate to inform each other what is happening in one and the other. Well, that's how they communicate. In fact, if the communication fails, the voltage will not only go up, or only go down, which would indicate a failure in one of the two units. And if this variation does not occur directly, it may be a problem with the processor, which is responsible for generating these pulses. What you are seeing here is not arbitrary. Well, yes, it is arbitrary because the manufacturer did it in his own way, but they are not meaningless pulses. The units understand each other, and there are many intermediate pulses that, if you look closely, change over time. That's how they communicate. But how does this communication take place? What parts are involved? What components do we find on the boards that help one communicate with the other? Well, we'll see that next, in the next video. Well, the communication signal from indoor to outdoor unit is produced through optocouplers. Why? Because we need long cables, which means that they will handle high voltages. And since the communication has to go from one microprocessor to another, to make that communication between high voltages and the processors, we need optocouplers that divide the area and do not produce any damage in case of a short circuit in the communication cable. That is why you will always find two optocouplers very close to the communication signal, placed just in the opposite position of each other. Notice that here we have a LED on the right, and on the other side of the optocoupler we have it on the left. There is always some voltage reduction resistor, diodes to prevent the flow of electrons from returning in the direction we do not want, and some filter capacitors. On this side we also have resistance, capacitor, and another diode. And notice that on the other side of the optocouplers we already have the tracks that will take us directly to the most complex part of the circuit, which eventually leads us to the microprocessor. The microprocessor communicates with another microprocessor, indoor and outdoor unit, through those optocouplers. This is the indoor unit. If the communication circuit fails, we have to check these optocouplers, these diodes, and these resistors, as you already know, and replace them. And the outdoor unit is exactly the same. Only that the outdoor unit is usually a bit more complex. Notice that here we have the pin where the communication cable is placed. We have some diodes, resistors, and on the other side we already have the optocouplers we were talking about. They are mounted in an SMD way, they are mounted superficially, their terminals do not pass through to the other side. But you can use the same optocouplers. What you have to do is cut the thinner terminals, and you can place them at these points, replacing the originals if they are damaged. They are a little smaller, but it does not matter. You can place, for example, the PC817. In the case of the diodes, you need to check their value, the resistors too, and the capacitors that are not in a short circuit. Well, this is how we are going to test. measure, and replace the components that are involved in the communication. What else do we have to do? Very important, follow the tracks. We always say the same thing, follow the tracks, always, no matter how long they are. Look at this case. We cross jumpers. We go around here outside. Look at the turn we are making. And here we will only be reaching the microprocessors. So, go over the tracks, follow the tracks, because they are cut and the communication stops, and we replace components and even want to replace the board, but we forgot to follow the tracks. It is like a cut cable. Please, let's follow the tracks in this part of the circuit. I will also show you another board from another brand so you can see how the components dedicated to communication are. Here we have a slightly more complex board. Here we have the red communication cable, filtering coils, a PTC, which is a small ceramic that opens with excess temperature, which you know, because we were talking in the sensor section, resistor, filtering capacitors, also a polyester capacitor, 2 diodes, and 2 optocouplers. The same in this case, we also have tracks that go from the optocouplers to the microprocessor. Let's see the indoor board of the same model. Communication cable, PTC, resistor, 2 diodes, 1 Zener diode, 3 resistors, capacitors, and optocouplers. Main component, always one on one side and the other on the other. Here we see the mark at point 1 and the mark at point 1. These are the components responsible for communication. If you find any problems, you need to check all of these pieces. I will show you a measurement on a working team as you would do at the customer's home. We will measure with the multimeter between S and N. Directly from the outside we can see if the communication is working or not. We have the same values that we saw just now on the test bench, 15, 4, 20, 15, 15, 4, 20, 15, and constantly a voltage that goes up and down, up and down. Always test between N and S. Well, these are the components that we will find in the signal communication part. In the next video, I will explain some more technical data and to keep in mind about these communication circuits. For this part, we need to go back to our famous drawings, diagrams. I will explain how this signal cable works. This cable is constantly powered by the line and neutral. We will use colors that we can understand better. We will use the color blue to talk about the neutral. And what else will we find? The famous optocouplers. We go to the indoor unit. These are a rather rustic diagram, but that's how it works and that's how you're going to understand it well and know why the data appears as it appears, and also understand how important it is that the parts are in good condition. Now I'll explain what I mean. What we are drawing here are the optocouplers, with the 4 optocouplers. 1 LED on one side, 1 receiver on the other. LED receiver, LED receiver. We will write or draw and read the line. Perfect. The electrons will always enter from the neutral side, and we will find diodes that will let us only pass one way, because this is alternating current. Each time I make a voltage derivation through the optocoupler, that voltage will go away, and this light will turn off. What does that mean? When the microprocessor, the integrated circuit of the outdoor unit, turns on the LED, the electrons go away, and this LED turns off, producing a pulse. Which, on the other side, in the circuit that works with 5V, this is from the indoor unit, the circuit will understand. The outdoor unit turns on the LED, the electrons are derived, the signal cable loses voltage, the LED of the indoor unit turns off and the receiver receives that pulse and the microprocessor, integrated circuit, understands it. This is how the outdoor unit communicates with the indoor unit. If we want to communicate the other way, from the indoor unit to the outdoor unit, what does it do? Well, the integrated circuit turns on this LED. The electrons are derived through here. This LED turns off and from the outdoor unit, with the 5 volts, that pulse is produced and the microprocessor understands it. This happens at different times. First they give time to one, then to another, and wait. One, another, and wait. One, another, and wait. And that is what we saw recently in the voltage that appeared to us over time. One, another, and wait. One, another, and wait. And this is how communication is produced. Units that work with higher voltages, that work between 30 and 50 volts, do so that if the cable is slightly defective, the cable does not cause any problems in communication. If we talk about a voltage of 3, the cable has to be in very good condition to work well. What are the most common causes of communication failures? For example, a cable in poor condition, with splices or joints. The S cable must be in perfect condition. And if you notice that there is an error in the communication, but that voltage variation is present, it may be that even though there is that pulse, the units are not understanding each other. Something you can do is, say this is the S terminal. You can add an extra cable, apart from the signal cable that it already has. And try to do it outside, away from the L and N cables. It is known that this generates a magnetism around the cable due to the high amperage consumed by the compressors. So try to pass a separate cable, a 1.5 mm cable, a section of 1.5 or 2 mm. Do not use coaxial cable, do not use anything strange, only copper cable. Make sure it is in good condition. Use a 1.5 or 2 mm copper cable in section, that is, thickness, square millimeters. This is a great test that solves many communication problems. Replacing or adding that signal cable is sometimes not the easiest thing, because passing a cable from the indoor unit to the outdoor unit is not easy. But sometimes it is the solution. Perfect. This is what has to do with the communication signal. This is how it is checked, how it is solved, how it is tested. Following tracks with patience, making these measurements, and you will detect any of those problems. One more thing to keep in mind, when you find a terminal with F1 and F2 cables, and use 2 cables to communicate, in general these units, which are usually the larger Samsung units, are using a different communication protocol. What does this mean? That communication is through a previously established coding. This means that the integrated circuits are communicating through a protocol, that is, they are communicating through a language established by another person. Different from the signal cable we talked about today, it is designed by each manufacturer with that pulse. In this case it is more complex because if the communication signal fails, it is not usually the cable, because the cable is included. In addition, they are very complex signals, very deep. So it is much more complicated to be able to measure. In case of communication failures in these units, in general, one of the 2 boards is damaged. In that case, they are damaged and no longer work. This is so that you know it exists, take it into account, know that it can appear to you, and do not be in the dark. Very well, this is what has to do with the communication signal. Let's keep moving forward.